Hello, everyone, and welcome to the chapter talk-throughs for From Social Science to Data Science by me, Bernie Hogan. This is Chapter 11, Introducing Natural Language Processing. Natural language processing has become a really popular and engaging part of data science. It's a way in which we can take text and do things with it like classify it, give it a score, extract keywords, and in the most advanced and extreme versions of it, be able to do things like query, extend, and make use of large language models. We know that ChatGPT has really taken the world by storm, and this is not really going to get us as far as ChatGPT. This is much more introductory sort of lectures, but if you want to understand how to get to there, it really pays to start with some of the basics and understanding what we do with text and how to turn text into data. So learning goals for today are first, get some simple ones, more in terms of the difference between like language and text. And then once we have text, thinking about how to break up text into words or tokens. We want to be able to eliminate potentially redundant characters or words. We want to show how text can be scored using a sentiment analysis package, and we're going to use Vader for that here. We're going to want to explore keywords extracted using TF-IDF. TF-IDF is a pretty old technique right now, but it's still actually very effective for being able to extract the most distinctive words within a large corpus. We're going to want to explore keywords using a classifier, and we're going to use a naive Bayes classifier. This is a pretty straightforward one as far as they go, although it's going to be notable how much wrangling is actually involved in order to get data from the shape that we have it in order to the shape that's required for this classifier. And we'll walk through some of that code and look at how we transform the data along the way. To begin, it's worth thinking about the difference between language and text. Language is how people communicate with each other. Language has meaning, it has cultural variation and context. Language can be accompanied by paralinguistic cues like pitch, where people raise their voice, and pace, where people speak faster than usual or slower than usual, potentially as ways to dramatize or provide emphasis. Yet, we don't encode all of those things all the time when we think about language. Rather, we encode language generally in terms of text. Now, text has its own features and variations, but whereas language is a means of communicating, text is data. Language is probably better considered information that can be encoded as text or as auditory signals. With the text, there are several key features that we would like to distinguish for encoding and for coding. So the first is that text has a sense of characters. Now, characters are the individual symbols that are used to represent language. So in English, we would have the letter A, where each of these, A and the lowercase a, and this one here in monospace, they're all the same character. At the same time, they're different glyphs. So a glyph is the way a character is represented. And so this uppercase A, lowercase, and monospace are different glyphs, even if they represent the same character. Now, the set of glyphs that you would use to represent characters is known as a font. So here in this presentation and in this book, we've been using Open Sans for most of the text, but when I've been using sort of system type text, I've been using Courier. Now, each of the characters is mapped onto a character point on a computer. So that way, even if we want to use symbols like emoji or different characters in a variety of languages with accents or perhaps pictograms and so forth, each one of them would have its own character with it, or a character point within a large set of possible characters. Now, as it happens, actually, the original character set that's used in the West is pretty small. It's the 128 characters of ASCII, or ASCII, but that, of course, is insufficient for work in a global world, or a globally interconnected world, where we would have text not only including things in English with emojis, but also text in a variety of languages and character sets. So an encoding is a way in which we describe those character points, and different programs, different coding systems, or different coding languages will be able to use encodings to a greater or lesser extent. It's worth noting that in Python 2, it's not Unicode by default. So if you try to type in a Unicode character, something outside of the smaller ASCII character set, or it might be a slightly larger Latin character set, but really definitely smaller than Unicode, then it'll throw an error. And it's actually a lot of work, as it happens, to make use of Unicode within Python 2. Now, Python 3 has been the de facto standard for a good 5 or 10 years, and it is Unicode by default. So that really simplifies a lot of the work that we would do in terms of getting data from the web that would be in a Unicode encoding. But we'll want to see how we can make use of that as we go along. Now, of course, as I mentioned there's many possible language characters beyond English, which we'll want to represent as bytes. Now, when we do that within Unicode, we might have a large map of millions of character points, many of which are not even used yet. It includes points for many characters around the world, from Arabic to Chinese. And it also includes emoji. Now, there's two main flavors of Unicode, UTF-8 and UTF-16. UTF-16 is not longer than UTF-8, but rather UTF-8 encodes emojis, encodes Unicode within 8-bit character strings, and then it kind of links them together. So if it only needs one such 8-bit character string, it's going to use it, but it might use 2 or 3, depending on where the character is in the character map. On the other hand, UTF-16 uses a 16-bit representation of that, and it's a bit larger, but you're always going to have characters of 16-bit size. But ultimately, they both represent the same Unicode character map. Now, here's an example of what that might look like in UTF-8. So each one of these would be a byte string. And as you can see, it's got this B in front of it to suggest it's a byte string. Now, in terms of bytes, that's what the computer would use. So that's an encoded version of a character. Now, what we would want to see is a decoded version, one that's decoded and made available for us. So you can see here that we have the Unicode for the Tears of Joy, and it looks like this. And when we decode it, then it's going to be this happy symbol. So we can print the happy symbol, but when we print the encoding, it looks back like that. So now by ensuring that your work is Unicode and that you can parse Unicode, you can definitely be more confident about capturing data outside of English and outside of the Latin character set. So now before we get to this, I just want to briefly go to the slides for today, or sorry, to the code for today. And as usual, what we're going to want to do here is, of course, restart the kernel and clear all outputs. Now we can have a sense here. Here's some ways that we can encode some things. And this was shown in the text. We can do hex. And now what hex is going to do is that's going to make this a hexadecimal digit. And so that digit, 0x1b, actually represents the number 27. So when we go back over here and you see this, these here are also hex digits, or they represent something in 16 numbers, or 8-bit. Now we can print here the letter A, if you'll notice, but also look when I print ORD A. ORD A gives it the number 97. So that actually means it's the 97th character point within this coding system. Now let's have a look, and we can print through the first 128 of these, but we're not going to print numbers 0 through 32 because they're all white space or otherwise reserved characters, and that doesn't really help out. In fact, it might even throw an error if we don't start from 33. Now you notice here they are, starting with 33, exclamation point, the quotes, and then we go on, and then we have the numbers, uppercase letters, some punctuation, and lowercase letters. And you can continue on that and explore what are the other sort of characters within the character point, but those are the basic 128 that you would use in ASCII. So for much of the rest of the chapter, we are going to be using the Stack Exchange data that was parsed as in Chapter 10. And in Chapter 10, we took that Stack Exchange data, we turned what was coming in as strings, much of it to numbers where it was supposed to be numbers. We took the text and removed all the HTML, we removed the links. And so then we're going to make use of that cleaned out data here today. You may recall from Chapter 10 that we had parsed some of the data from the movie Stack Exchange and then saved that in some file format. In the book, I mentioned Pickle, but more recently I've been using Feather and tend to recommend that because it works quite well across different versions of Python. Now, instead of going back, in case you haven't done that, trying to clean the data yourself by hand, you can use the Stack Exchange downloader that I've provided in the supplemental downloads folder. Now, to import the file once you have it, then you could get your pathlib, import pandas, and then you can see here what I've done is get the data directory, and this is where it should go if you use the Stack Exchange data. It'll go in the directory above and over data, and then underneath it unzips the Stack Exchange archive, puts a bunch of XML in there, and that's also where it puts the data in Feather or in Pickle. Now, as it turns out, it is easy right now to use pd.read pickle rather than importing pickle and then parsing that into a data frame. But as you'll notice here, I use posts.feather. Now, to refresh as well, that's over here in the Stack downloader. And as you can see, it's just one very long cell that when we run it, it will load the list of Stack Exchanges, and you can select one. So of course for the book we selected movies, but you might want to select a different one. Movies is going to be a bit slow to process, but it will give kind of the consistent results that we'll see later on. Then when you select that, and you can process it like so. Now we won't be using the users.xml data frame. You don't need to process that. And if you've already downloaded this file and process this, when you select download, it will just include the additional data. It won't download it again, and that's to help speed things up as well as lighten our footprint on the Internet Archive. So now before we get to the specifics of Stack Exchange, I wanted to use some toy examples to show some of the basic cleaning steps that we're going to do. And then later on you'll see that I've put these cleaning steps into a method that we use to produce a clean text cell for each of the cells in the Stack Exchange data that we're interested in. So in this case, for the NLP workflow, we're not going to be doing a lot of analysis here, or certainly not a lot of interpretation of the analysis. We're going to want to leave that to you, but we're going to do kind of the stuff before that, which is just the skills for three really core tasks that you tend to see within an NLP workflow. Those are scoring text, classifying text, and extracting keywords. Now, they really scratch the surface of what's available in NLP, which is a really, really deep field and one where there's a lot of work happening actively in all dimensions, from these forms here of scoring, classifying, extracting, but also putting that together in large language models and then interrogating those language models. Now, I mentioned down here, you would then consider how to place these within an inductive or a deductive framework to explain some phenomena within text. Now, why would I mention that in this case or highlight that in this case? It's partially because when we extract text, we can do this in a very deductive way where we have a hypothesis-driven framework, but we can also do it in an inductive way where what we're doing is trying to make sense of the text and using things like keywords or scores can help us kind of explore what we might want to find in that text rather than just test a hypothesis from the get-go. But before we do any of that stuff, we're going to want to make sure that our text is ready for such analysis. Now, while Chapter 10 cleaned the data, it really cleaned it just to the point of taking an XML and then putting it in a data frame, giving it the right type of columns, stripping out some HTML. It turns out for NLP that that's not really sufficient for a workflow, and there's a couple other ways in which we're going to want to clean that text before we do some analysis on it. So the first one is that we're going to want to think about tokenizing the text. Now, tokenizing is a way in which we chop up text into words or smaller chunks. It's typically words, but there are more nuanced ways of doing tokenizing on like parts of words that you'll see in more advanced models. Here we're just going to look at them as words. Now, the simplest way to do that in English is to break up by spaces. Now, that's not available in every language, and for some languages, tokenizing can actually be quite a complex process, for which nowadays we're using large language models for things like Arabic, where it's important to know the context of the words because they often, the words kind of flow nicely together, and then you can split them up in ways that make sense from the words, but aren't necessarily the case for spaces in Arabic. So in English, we'll do that using a tokenizer. Now, a tokenizer can be simple and it can be more complex depending on the needs. One thing that we'll want to consider is something like punctuation. Now, in addition to that, English has a number of common and often uninformative words. These are found in a stop words list that you can exclude unless warranted. So, for example, the stop words list might have pronouns in there like he, she, or they, but you may want to not exclude those words depending on your subject of interest, but generally it will exclude those as well as the words of and the and you can see that whole stop word list in Python, and we'll show that now in a bit. Now, when we tokenize and we split that into little units, we don't just have to tokenize by one word. Now, to do that, that's called a unigram. But we can have pairs of tokens and use that as bigrams. Now, bigrams are often useful if we, or trigrams if we have words like University of Oxford. It's not just university, it's not just Oxford, but it's that whole word together. And if you tokenize, you won't necessarily get that as a single token, even if it is a single name for a single place. So now here we have a stylized example, classic from Dickens. It was the best of times, it was the worst of times. And we can see here that within that there's a lot of redundancy in this sentence right here, but also the redundancy creates a sense of poetry to it, but it might not create a sense of being maximally informative. So here we have a list, and we've broken up all our tokens. Now you notice that we have times here with a comma and times here with a period. Now in order to indicate that those are the same word, times, we might want to get rid of the punctuation. And so we take our tokens and we can strip the punctuation. Now once we've done that, we can see times and times are pretty well sorted. But what about it and lowercase it? Now in this case, we don't think of the word it as having a kind of a semantic meaning on its own in the uppercase. If you were doing work on the Addams Family, the show The Addams Family, or the movie, or the more recent television show Wednesday, there's a character called Cousin It. Now, Cousin It is a proper name with the uppercase I and T. So you would want to be careful to distinguish Cousin It from just the word it as it has here. Now, we're not going to do that in this lecture, but that's an example of how we want to ensure that when we do use lower punctuation, it's for a meaning, to make sure our words are comparable. Now, once we have them in lowercase, as you can see here, now all of our words are all right, but we have a bunch of stop words in there that aren't really very informative. And so if we remove them, what we're left with is best times, worst times. Now, of course, we can reduce that even further down to best times, worst. But just in that order right there, best times, worst times. But despite the paucity of information that's there, this still really signals the original phrase. As it happens, if you put this into a search engine, you will almost certainly come up with the Dickens quote as the top or the second to top entry. Now let's go have a look at how we might do some of these things in JupyterLab. So come on over here from text to language, and you can see what we've got done here. I've loaded up the StackDF, and this is using the more simple code, but I've provided the some of the older pickle code there in case you want to use that instead, although I really do recommend downloading it through this way or doing it yourself in a way that's like that, and then getting a Feather document. You'll also notice that down below I use the updated variable names. So where the older variable names had, I think, one called clean body, now we have one called body text, which is more in keeping with the rest of the variables. It's really from Stack Exchange, which would have a descriptor and then the type of the variable as the name of it. Things like post ID or creation date. So I run this, and Feather is now imported. Okay, so let's have a look at the word tokenization to start here. Now I've imported pandas again, because you'll notice that when we split by a hyphen there, or sorry, split by a space, I turn this into a series, because this is just going to be a list. Then we can get some value counts. So we see here, was the of it times best. And so times with the commas there one, and times is there one, which really means that it's it's not capturing these things as being comparable. So now we've split in this case by space, but there actually can be some more thoughtful ways of tokenizing this. Unfortunately, we can draw upon packages for that. And in this lecture, I'm going to be using the NLTK package. The NLTK book hasn't been updated for some years, but the package is still continually updated, and there is a version of the book online about the NLTK package and using the more updated Python 3 that you can see and browse freely yourself. So I'm going to load that up, wordpunc.tokenize, and that means we're going to tokenize and consider punctuation as part of our tokenization. So let's see here. Now when we print this series, we have it, best, times, comma. You see now comma becomes its own entry, but times, there's now two of them, and there's worst. It did not conflate the two words by case there, because as mentioned earlier in the cousin it example, that these may be semantically different, and it doesn't want to make that assumption in the tokenization. Now down then, the next thing was the stop words. And so again, you can see here we have NLTK download stop words, and from corpus import stop words. Now I don't need to do this. I've already imported NLTK, and I've already downloaded that. But in case you want to do that yourself, you do that here, downloading package stop words, and it's already up to date. So now it says stop words are the set of stop words in English. Now right here. So then if we look like at this, it's what we're doing is we're just filtering out the words if they're not stop words. And also we just want to make sure that the words are alphanumeric. So that way we get rid of this comma up here, and then we can have a look now. And you can see what we've done is we've first made all the words lowercase. We've made sure that they're all punctuate or not punctuation. And again, we get two of the times and best words. So we really kind of whittled down that text to its main core. Now, as with many languages, English has a notion of things like verb conjugation, where you may have one verb for a present tense or a past tense or a future tense. So we have like bark, barked, and barking. They're all part of the verb to bark. And in this case, and I think in the book, I give an example of a dog barking at some tree bark, which is one of the ways in which we might think of not only are they the same word, but there's also words that are nouns and verbs with the same word. In fact, the word run has many, many different meanings and is available as both a noun and a verb, and I think other parts of speech as well. So the way we want to do this, we might use a stemmer. So a stemmer here, you have this ed and the ing, and what we're going to do is take that out so that each one of these all ends up like that word. And so you can see here from the we use the Porter stemmer. You don't have to use this stemmer, but it's a pretty standard one. And then you can see for the stem list, what we're doing is we're just filtering it down to the stemmed version of the words. And you see here, well, what if your dog is barking at the bark of a tree? Now that's a problem for a stemmer because it's going to conflate the two different versions of bark. But at the same time, we've had ways to consider this, and one of them, which is might consider a bit more advanced than stemming, is lemmatization. Now what that does is it accounts for parts of speech, like noun and verb. So now you can see down here that instead of a stemmer, we've imported a lemmatizer. Now the lemmatizer takes a little bit longer to run because it has to think about the words in relation to a model of them. Now down here you'll see one of the options is V. That means we're going to care about verbs or distinguish verbs in our tokens. And so the Jupyter Lab little icon there suggested we should go down and check this out. So here we have the Porter stemmer. Now this is a pretty contrived example, but I tried to do one where you could think for a stemmer, things like office, official, officially, officer, they all mean different things. And yet, if we use a stemmer, they're probably all going to show up as like office or OFFIC as the stem of that word. But let's have a look. Okay, as you can see there's OFFIC, but then there's OFFICI. So it's kind of distinguished one of them as official, and then the rest of these as office in some way. But the words themselves are not really indicative of real words. They're kind of just truncated to the point where we can distinguish them. And so when you look at them later on, it might be hard to interpret what you're doing. Now instead, so if we use a lematizer, and here's an example of one, we would download the WordNet for the lematizer right here. If you already have that available, of course you don't need to. And now we instantiate that as an object. So we have a lematizer, and now we have a data frame of our words, and then we're going to map that data frame. So or actually the series within the data frame for word, and we're going to use the lematizer, wlemma, see, dot lematize, care about the verb position. And now let's have a look at that. Now the reason why I did this bit of wrangling right here and made it a series rather than just a list is so that we can compare the word to its lemmatized form. Well, I think that looks kind of useful here. We can see running and its lemma is run. Office and its lemma is not offic, O-F-F-I-C, but just office. And so similarly there, we had all these words. Ran became run, so it conjugated rather than chopped off like running or whatever. Huge tab, victory party, offices, officially, and trouble. So it's a little bit more sensible, a little bit more like natural language, and does seem to distinguish some of the different words here pretty effectively. So now if we have the words already cleaned and ready for us to do some analysis with, then here are the three different kinds of analyses that I'd like to introduce. The first one is scoring documents, and we're going to do that with the sentiment analysis. Now, there's a variety of ways in which you can score documents. Sentiment analysis has become a relatively popular one. It's not universally loved, and it's not universally adopted. And that's because the way in which we score with sentiment analysis is often lexical, which means we refer to it as specific to a word. So the sentiment analysis that we can use can have a score for each word, and then that scores, and maybe you would count up the scores for each word. Maybe a word represents something happy or sad, or maybe a word represents something that asserts a belief or asserts a fact or asserts a level of uncertainty. And you count them up and maybe sum them or average them depending on the algorithm, and you have a score for your text. Now, the reason why it's not universally loved is that the notion of a word being positive or negative can be very context specific, and simply just adding them up may not do a very good job of capturing the nuance of that. And we'll see some of that in the examples. However, in a really large corpus, it can still be very useful for distinguishing data. So one sentiment analysis program that's commonly used and that we'll be using here is called Vader. Now, one of the reasons that we are using Vader here is because it's free, it's easily available. Pip install Vader, but it is a bit simplified. On the other hand, going and checking out the Vader paper is quite recommended, because you'll see how they came up with this and why they decided to develop a sentiment analysis in this way. To give kind of the short version of that is that they were looking for a sentiment analysis algorithm which would account for the way that text is often presented in short form, like in comments or on Twitter. In forms like that, things like all caps for one word or lots of words make a difference. Things like saying yay or yay with lots of Y's at the end, that repeating thing, may also make a difference as well. And so Vader can be pretty clever about these things. The actual scoring for the sentiment in Vader was done through crowdsourced workers, so asking, is this word a positive word or a negative word? And then it was put together as this model that you can use to score text. The way it scores text is to give it polarity scores. It gives it 4 scores, a positive, a neutral, and negative score, and then a compound score, which is a combination of all of those different scores in a weighted way. So here we have an example. Wow, I'm feeling great today. The weather is lovely. Hooray! And here you can see we have a really positive score. The top value would be out of 1, and most of the share of that top value is actually gone to positive. None is gone to negative, and only a little bit to neutral. So this is a pretty happy statement according to Vader. So let's look at how we could do that in Python. So come over here. First, we're going to import Vader there. I've got the more involved import statement here where we look for pip with the sys executable. Now you can also generally get away with exclamation point pip install Vader, and so forth. But there are times, depending on when you're in a virtual environment or another using multiple Python kernels, where you might not be confident. And so using this script can really make sure that Vader is installed in the right version of Python. But normally it should work pretty well with just pip. Okay, so here we, from the Vader sentiment library, we import the Vader sentiment package. And in there, actually, we're looking at the sentiment intensity analyzer. So because we've imported it from this, we don't say Vader sentiment dot sentiment intensity analyzer. We just call it that. And so this becomes an object that we'll use in order to get the scores from this text. Now I have 4 texts right here, and they're written in a deliberate way. They're a bit contrived, but I think in English we would get the meaning of them. And the reason that I use them in this way that's contrived is because, well, as you can see here from the sentiment, in the top one, well, I'm feeling great today. The weather, this is again the very positive one. But now let's have a look here. This is a much more qualified statement. I would be lying if I said this was a really bad day. Now that doesn't necessarily mean it's a good day, but it probably means it's not that much of a bad day. In fact, it might be quite neutral. But you'll notice that it actually also put in a little bit of negative. It caught that as half negative. Now, is it really negative? I'm not sure. On the other hand, this one says, I would not be lying if I said this was a really bad day. Now, if you think about that in your head, it says, it is true that this is a really bad day, which therefore means it's generally negative. But because of the way that it's like roundabout with clauses of this, I would not be lying if, which is a clause in this case, it kind of confuses the sentiment analyzer a little bit. And so it ends up, again, thinking that it's very neutral. And if you'll apologize me for the cringy, if you will, nature of this particular phrase right here, I think it's meant to illustrate how language can be used in ways that are really counter to what you might expect if you're using them in a very straightforward and surface way. So we say here, hey bro, those sick beats brought down the house. Now the word sick in this case is generally perceived as negative, but in our case, we mean sick as in very good, like, ooh, those are sick beats, and so forth. And brought down the house, similarly, is an aphorism for made everybody excited, or it was a really big party, but yet brought down, or bringing down a house might, in a very superficial sense, seems like a terrible idea. So in this case, we see here negative and neutral, when in fact it's really supposed to be very positive. So this is just showing that while this sentiment analyzer can be very good, it's mainly good for text that is quite straightforward and direct. Whereas as soon as text starts getting more local to a particular culture, as soon as text starts getting more qualified, then this can get a bit difficult. That's not to say that NLP can't handle this, but that it's worth caution in using a relatively simple text analyzer that's lexical and additive, rather than one that's more nuanced about the meaning of these words in different circumstances. Okay, so now we're going to do this for the entire stack data frame. So you recall that we've loaded that stack data frame, and I'm going to only sample 2,000 of the rows, just any 2,000 at all right here. But you'll notice that for that sample, I use the random state of 1, 2, 3, 4, 5. So the random state in this case is the same as a seed. So that means it's always going to sample from the same rows in the same way to make this code replicable. Now that being said, I have re-downloaded the Stack Exchange now, and this is in October of 2023. So it will always give the similar sample for that particular version of the Stack Exchange, but that particular version is a more recent version than the one in the book. So we'll see different rows down below when we sample. Now this here, I use Cinti SR, and I'll say that it equals body text. Now you might have seen that as like clean body or something elsewhere, but we're using body text. That's the one that's we've taken the text from the posts, and we've now extracted the XML and the URLs from there. So we're just left with the text. Now it's not necessarily cleaned text, but we don't necessarily want clean text for this. In terms of a sentiment analyzer, things like these 3 punctuation marks, Vader will consider, and it will consider uppercase or all caps as a booster of intensity. So for this one, we got to be careful how we clean the text before we go off and score it. Now you might be wondering what I've done down here after that, but you'll see what we've done is we get this dictionary back. And so instead of just calling it a dictionary, I'm using JSON normalize in order to turn that into a single data frame. Then what I do with this single data frame is I also am able to use an index value there, and then I concatenate that data frame with our existing data. So now we're going to have sample df below this, which is no longer going to be the stack data frame, but it's going to be an extended data frame with the sentiment analysis scores. You'll see there that's because it's only got these 2,000 here. And I didn't want to add that back to the original data, considering I just was interested in that sample for now. Now you can run this with the entire data frame, it will take a little bit of time. And to remind, if you're curious about how much time it's going to take on your computer, you can always go %% time, and it will report on the time at the end. So let's go and have a look to do that here now. So on my computer, it took about a second to do that for the 2000. I'm pretty fortunate to have a kind of a newer computer. It may be a bit faster or maybe a bit slower depending on your computer, but that really illustrates if it's 2000 for 1 second, this will take 10, 15, 20 seconds for the entire data set. While that may be appropriate for your analytical work, just for illustration, I don't think it's necessary. Now down here I haven't displayed the entire data set. I used head, which will just display the top 5 rows. And then I said body text, positive and negative. So this is the body text right here. And we can see this is all speculation, but blah, 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 blah. Now it's not really the most useful just to see that ellipsis there, but that is the default column width for body text and for a display. I can't recall. I believe that might be 30, 40 characters. But if you want to extend those characters in display, rather than, say, making body text a series so that it prints it in like monospace text, you can do this. Set option, display max call width. You'll see this is now 1,000 characters, and that's much longer than this one, and probably too long for our data set, but it will be able to show a lot more of the comments. In fact, I'm not going to go all the way there. We'll do 2,000 instead, or 200. So we can see here, this is all just speculation with some points to consider. How many? This is kind of interesting. I don't know why it's intended to be a drama, but it's Kubrick rated, so it's the movie. It's the movie one, and we can see here our positive score and our negative score. And in a lot of these, it's quite neutral. This is a question and answer forum, and so I wouldn't really have a prior expectation about whether people are really negative, perhaps if they're criticizing some new film in a franchise, or really positive, where they're trying to extol the virtues of a film. But in this case, in this sample, things are pretty neutral, pretty near the middle. And you can see that from some of the way the text is described. I'm currently doing an analysis on this. I'm trying to figure out why Trevor's working. And so it's quite neutral, quite reflective. Now, what I haven't shown here in the text, but I hope it would be somewhat obvious, although it's worth pointing out. These are now series in our data frame, so we can plot them. We can do things like correlate one with the other. Is positive and negative anti-correlated, which would say that people are either happy or sad, or is it positively correlated relative to neutral, which means that there's going to be lots of ambivalence, people that are expressing both a lot of strong positive and negative emotions rather than being neutral. We can explore that or other issues, but now we have a column of data in which to do so, and so that's scoring that data. The second of these approaches to show off here is TF-IDF. Now this is a classic technique to capture keywords from documents. It works well with a large series of documents because it's able to then estimate more effectively words that show up in a few documents, but not all of them. And those words that show up in a few documents, but not all of them, tend to really distinguish those specific documents from the rest. So if we were just to count the number of words in a document, you would get a lot of the and of and really common words. But if you use TF-IDF, then you get a lot of distinctive words. And so we'll see how that might be useful with our Stack Exchange data now in a minute. The first thing to note, though, is what does it stand for? TF is the term frequency. So for each of the words, we just have a count for how common those words are in all of the data. Uh, but then we look at inverse document frequency, which is a formula for calculating how uncommon words are across the documents. And so you can check the Jupyter Notebook for the full code for this right here. But the steps to go through are use a preferred way to tokenize each document into a list of words. So first off, if you don't care about the capitalization, say of the word movie, then you'd want to make sure it's all consistent, perhaps all lowercase. Then we're going to use the TF-IDF vectorizer, and I'll show that code now in a second here. That's from the scikit-learn package, I believe. And what that does is it transforms the documents into a word-by-document matrix. So this is also the start of where we are introducing the means by which we transform data into a matrix format and then work with it in the matrix format. You'll see stuff like this as well later on in the network chapter, where you can have a matrix of from and to. So people send a tie from themselves to maybe the person they're replying to, or to someone else if there's a friendship. But in this case, we have a matrix of words and documents. Now, it's also worth noting then that depending on the size of that matrix, it could be pretty big. So if we only use a sample of 2,000 documents, in this case comments, that would be still 2,000 columns. And so if we're looking at all of the words in those columns, it could be thousands of words when we combine all the words across all the documents. So it can be really big matrix. Working with that matrix takes up a lot of memory. And so this is also where we start thinking about optimization. Now, in this case, I'm going to be a bit lightweight with optimization and just say, let's filter down to 2,000. But later on, you may want to explore ways in order to do that optimization a little more thoughtfully. So now what we do once we have that matrix and that vectorizer, we're going to get scores for how common a word is in each of the documents. And then we sum them up at the bottom of that, and that's going to be our TF-IDF score. Now we can rank that score from the highest to the lowest, and that'll be words that are the most distinctive at the top and the words that are least distinctive at the bottom. As a convenience, if you want to practice this section right here, I've put all the words for importing that here. And now you'll also notice that what I've done is created a method. Now this method's pretty slow. I've tried to optimize it a little bit. I think I'd hopefully be able to take another crack at it some other time, but it's pretty much exactly as we see in the book still. I've tried things like multiprocessing. It doesn't really help. And so we'll see that in a minute. But for now, first let's import these. Here we have a lemmatizer, stop words, tokenize, and a vectorizer. So as you can see, this is this workflow right here where we take our text and then we lemmatize it or tokenize it, then lemmatize it, then get rid of the stop words. And so we only have distinctive words left, like best, worst, and times, and then see how often those show up in different documents. So I'm going to run this function here. It's not going to do anything, of course, until we make use of it. And we can do that down here. So we have our sample DF, remember that's the 2,000 ones, and we have a column in there called body text. And so we're going to map clean text, this function right here, onto documents. Now we're not going to put this back into our data frame. We're just going to have this clean text as documents, and that's going to be just a long array of documents. And then we will make use of just that array. Let's have a look at that. And you notice I've put a time up there because it is going to take some time. Even on my computer here now, 2,000 of those is a bit slow. I mean, it was 6 seconds for that. I tried doing it with the whole data set, and I just kind of ran out of patience, really, because I believe there's 50, 60,000 documents in here. And while, again, that might be really important for your own research question, it's not so useful just for the point of this exercise. So here's our vectorizer down here, once again, just to highlight that. That's what we do. It's a sklearn feature. And then here's what we do is we just instantiate it as an object, and when it's away, and that object will take in a object, in this case a collection or an array of documents, and then transform it. And this fit transform method right here takes a document, which again, one-dimensional array, and then it's going to, like here, we say fit transform to dense. I tend to just use this as the canned text, that will then create a dense matrix of the the words down as rows and the documents as columns, and that's going to be our word matrix right here, which I've called word map. And so here, let's have a look at that vectorizer. First, I want to print the directory of the vectorizer. Oh, let me run that, of course. And you can see here's all the different things that you can do with that vectorizer. Now, I've done a bit of the pre-processing myself by hand, but you can see that vectorizer also has things like a build preprocessor, build tokenizer, so you can really dig deep into the sklearn package and the vectorizing stuff itself in order to create a workflow. Now, next to that, I wanted to print WordMat and see what is WordMat, what's it going to look like. And so you see here, it's a fit transform to dense, and this right here is a matrix. So it's just an array of arrays. Now, as it happens, you know what else is an array of arrays? An array. Now, not to be flippant about that, but rather, you will see in some of the documentation that they're phasing out the matrix format because it does seem a bit redundant when you can just have arrays nested in their own arrays. But nevertheless, we're going to use a matrix right here because that code works. And I do want to highlight some things about it, though. Well, first of all, we see TF-IDF scores equals wordmat sum. Now, if we print up here, you'll see that those are all zeros. But actually, it's not all zeros in this matrix. It just so happens that the first word didn't show up in the first three or the last three documents, and the second word didn't show up in the first three or the last three documents. But when we sum them all up, we're not going to get zero. We're going to get those words having some sort of TF-IDF score. So first, let me just print that score here, and I'll show you what that looks like. And there we are. We have an array or a matrix, a one-dimensional matrix of scores. So we just have this one array inside of it. So the first word has a score of 181. The second word has a score of 100, 1.9, and so forth and so forth. So then now we have these scores, we can rank order them so that the score that is, at the top would be the most distinctive. But of course, if we just sort this array, how do we know what word that is in the 0th position or the first position? We'll get to that now in a sec. But first I want to show you just this little bit of code here that you'll see down here, TF-IDF scores.a1. And you'll notice, just have a look at the difference between those two here. The one up top is a matrix with an array inside of it, and this .a1, what it does is just flattens that, as it's called, and so it just turns it into this simple matrix that we can use. Now, I did mention, what about the names for the words? And so we have here a word list, which is vectorizer.getFeatureNamesOut. So that will be a word list, the same dimension as the scores. So the 0th entry will be that one. Now we can have a look at that word list right here, and let's just see that if I run that. And so the first word is AA, and the second word is AAMIR. You can see it's sorted those. The last words here are not in English, and that's sorted in that way because these glyphs are further along in the character set than the ABCD words. But that's how they're sorted, which is by the Unicode character set or character point. So now we have our word list right here. Then we can use that as the index. So we have this right here, this flattened matrix, and then we're going to make a series. So this is going to be the first row, and that's going to be the index of the first row, second row, index of the second row down here, and now we can just display them. So here's the top 10 words. And would you look at that? From the movie database, what is the top word? Movie. And the second word is film. So I think it does actually a pretty good job here of extracting some keywords. Indeed, the fifth word is show, and then make. Now, they're not all super descriptive right here. One and see and say. I don't know that they're the most distinctive words in this particular set, but they would also give us some clues as to how to interpret this particular data set. Now, would and could are sort of words of aspiration or belief, and so having them up there rather than does or will may itself be a cue as to how they're talking about movies within this particular data set. Now, the last topic for this section on NLP is classifying text. Now, classifying text and categorizing text are two slightly different approaches. To categorize text, you would have a pre-existing list. So, for example, you might have a list of color words, and so you can categorize a word as being a color or not a color. But that's because the list of them is predefined ahead of time, and we just filter the words in a rational way into either of those categories. On the other hand, classifying text is when we might do that split and do that ourselves based on some criteria within the text, some quality of the text as data. Now, generally speaking, what we want for a good classification is that there's more in common in the different sets than between the different sets. So if we classify posts, then we might think what we want to do is classify them so we know which post is a question and which post is an answer. And indeed, that's what we're going to do now in a minute. But you might find some other interesting or meaningful ways to classify this. A really common one, of course, would be anytime you can have two polarities, so like left wing and right wing, or authoritarian and libertarian, happy or sad, and so forth. So that leads us to the first kind of classification, which is a binary classification. So each document gets a true or false value. Now, it doesn't have to be true or false. It can be up or down, but it's really just exclusive values. And what we will do is then say whether the document exhibits that feature, which is true, or doesn't exhibit that feature, which is false. So within a binary classification, we might do that with a human coder. So we might have someone code this word as, does this document contain factual information? Or does this document contain hate speech? The documents, of course, would have a true or a false value. Now, of course, we don't just want to classify words in true or false or into one bucket or another. There could be lots of instances where things are in multiple different buckets. And we might say that that's a form of multinomial classification. So we might be able to classify the documents into one of groups like news, opinion, weather, sports. You read the different sections of the paper, label them by that, and then train a classifier so that when it reads a story about rain happening, it knows that maybe it's weather, but it might also have other things involved, like because rain is happening, there was a flood, and then that becomes a news story. Now, we can have classifications that are mutually exclusive, or we can have classifications that are overlapping. So if it's overlapping, we might give a document a score on how much it meets or satisfies or correlates with one part of the classification or one group, and how much it scores with another one. So we might give our multinomial classification here a score out of 1 for how much it's like news, how much it's like opinion, and how much it's like weather. That being said, it's very common, very conventional to then find a cut point within that overlapping distribution. So we say, how much are you overlapping in one or the other? And we're just going to pick one side, and you're going to be on this side or that side, depending on where you fall in this distribution. So what we won't get into in this tutorial, but you should look for new videos or other videos beyond the chapters where I might end up discussing this, is an embedding-based classification. So an embedding-based classification either has a pre-existing model or it trains a model on all of the documents. Then each of the tokens, either their words or phonemes or whatnot, will have some place in a big network of words that are associated with each other. So we might think, for example, of the word food, and then we have the word grow and the word cook. Now, grow and cook might not be too close to each other, but they would certainly be close to the word food. Now, where would the word chef go? The word chef is related to food, certainly, but it might be a little closer to cook than it is to grow. That's not to say that chefs don't grow their own food, but we think of chefs as preparing food rather than the ones who are growing food, which we might think of in terms of, say, a farmer or a hobbyist or whatnot. And so what an embedding is it's a long series of numbers that represent where the word is in this abstract latent space that's been already prepared. And then you can take two words and give them a score in that space, but the score is not going to be one number. It's going to be a series of a lot of numbers. Uh, and then another word is going to have a series of a lot of numbers. And then you can plot them in and start to look at more abstract features like which words kind of cluster in the same way, or whether there's some words that seem to bridge between different parts of the latent space. In order to do that, you have to have a model, and you can create those naively with programs like Word2Vec, or you can use a pre-trained model, which has already been trained on a whole bunch of data and has a sense of which words are related to each other. A classic one of those right now is the model BERT, or bidirectional encoding for representational transfer, or just BERT. Now, that's a masking model. So what it's trained on is it has a sentence like, the blank was delicious. And, if you have that, what word would go in blank? And I guess the best guess would be the word food, but you might also say that the salad was delicious, or so forth. So it's not only the word food, but it kind of gives a best guess. Now, GPT-3, on the other hand, doesn't it's not a word masking model, although you can work with it like that, or GPT-4, other sort of LLM models like that. But instead, you can get back just the vector itself from the LLM, or you can just query it and get back additional words or data. Because GPT-3 and later versions of GPT have been rolled into ChatGPT, a lot of people might think of it as merely a model where you send up text and then you get back text. But rather, what's happened is that you send up text, the text gets tokenized, it then gets turned into an embedding in this model space, and then that embedding is used and worked through the model. But for all of these, you're then going to want to score afterwards, and then we're going to want to look at that score and see maybe how accurate it is or how effectively it classifies the material. So one of the earliest ways, or one of the more straightforward ways to do this, is to use naive Bayes clustering. And that's one where we're going to train our own classifier and then apply that to the data. So this will allow us to classify new documents that we've not already seen. And so in order to do that, we're going to want to divide the data into multiple sets. So first is the training data. We're going to want to train on this data, and that's going to give us a sense of the probabilities of certain words as they appear in the data. Do we commonly see this word in this group of text? Do we commonly see this word in that group of text? Then we're going to want to test that data. And so we can then take part of our data and then apply those probabilities to the testing data. Now, if the words show up in the testing data in the same sort of pattern with the same sort of probabilities as in our training data, then chances are our training data has worked really well and can be very accurate to help us delineate our testing data. Now, we have a third set of data, and that's called our holdout data. And we don't always use holdout data, but part of the point of training a classifier is that you would be able to apply it to some new set of data or something we might consider out of sample. Now, the reason why we distinguish between training, testing, and holdout, why not just have training and testing data? Well, the thing is that you can, in many subsequent downstream versions, not just in naive Bayes classifiers, but in later ones, you may train the classifier over multiple iterations. So you might train on a random sample of 60, 80% of the data, and then test on another 20% of the data, and then take another random sample and do that again, and then take another random sample and do that again. And as you iterate through these, no given sample is going to have too much leverage on the overall score. But that's how we alternate between training and testing data. At all times, we want to keep some extra data as our holdout data that we can apply that classifier to. So in the book, we take we take 2,000 rows of the Stack Exchange data, and you'll notice here that for the book, I've taken the first 1,000 for training, and then the next 1,000 for test data. Now, do you really need to have this split so evenly? Not really. You can train on 80% and test on 20%, or even 90 and 10%, depending on the size of your data. In fact, we're going to go and look at that data now and see what happens when we vary the size of the training and test samples. Now, what we do here finally is get an accuracy score. Now, there is a real subtlety to accuracy scores, which I would encourage you to explore in terms of things like specificity or sensitivity about whether the things that we classify as correct are only the things that we want or all of the things that we want. But those numbers, only the things that we want or all of the things, including the things that we want, uh, it get combined into an accuracy score here. And so we can read that as the percent which had their labels predicted correctly in this instance. So let's show how to do that with a naive Bayes classifier. It's going to train on words that are, and the reason it's naive is it doesn't really think about a lot of the interrelationship between the different features. It just has like maybe a column for each feature. And does the feature appear in this document? Yes or no. Does it feature in this document? Yes or no. And then it combines all the scores for all of those documents in order to get a probability that we'll see each word in each document. And then we use that set of probabilities applied to our test data. So with a naive Bayes classifier, the bog standard, the simplified version of it, it just uses two classes, and that's why we have a true or a false. So the document then becomes a vector of tokens for words that do or do not appear. Let's have a look at what that data looks like. So we could have a feature list, and instead of having, I was wondering about the reference where that director in the movie is saying something or other, blah, blah, blah. So we would have these words here, director, movie, wondering, reference. And in this first row, this represents one comment. And that one comment or one post is a question. And it features the word director, it features the word movie, it features the word wondering, it doesn't feature the word reference. Reference is actually featured in none of these words right here, but we would assume that it's featured in at least one of the documents because it ended up in our set of tokens. Now, on the other hand, director shows in this question, but not in these right here, and the only word that shows up in this answer is movie. So you can see you can build a lot of these, but also it's worth noting that this means that you're going to have this kind of dictionary. We're going to have one dictionary for each document, and the size of the dictionary is going to be proportionate to our feature list. So if we take every possible word in every possible combination, we're going to have a really big, really long feature list, and that's actually going to be pretty slow. So instead, we should find a way to whittle down our text. Now we'll see how I do that here, but I would like to encourage you to think about a more thoughtful way to do that, and we'll give a sense of how we might do that at the end. So here's some code here. Train set and test set means we're first going to take the first 1,000 up to the first 1,000, and then we're going to take the remainder because we've already subsetted this to 2,000 rows. So here's a train set, here's a test set. You'll look here, we just train on the test set, and then we can print the accuracy. Now, once we've performed this classifier where we trained and then we test on our test set, then we can print the accuracy. And so this might be a score of 6, 7, which would imply that 2/3 of the time it classified the text correctly, and 1/3 of the time it didn't. To be fair, 2/3 accuracy on a when like totally random is 50% accuracy. That means half the time it gets it right, half the time it gets it wrong. You know, 2/3 is not great. But we could probably improve that somewhat. And in this case, I used a really naive Bayes classifier. But ideally, you would want, certainly for a binary variable, you'd probably want some classification even higher than that, or much higher than that, unless classifying text into one side or the other is really, really difficult, in which case maybe 0.67 is worthy of consideration. Now let's look at how we might do this in Python. And one of the things that I want to pay attention to right here is how we get our data into this particular shape right here from simply an array of text documents. Okay, so from NLTK, I'm going to import the naive Bayes classifier. You'll see here what I've done is I've filtered the stack data frame first down to just questions and then just answers. And so what we have down here is post type ID and body text. That's really all we're going to want here is just whether it's a question or an answer, and just the text. And then I just take the first 2,000 of them. Now, before we do the classifier, we're going to want to tokenize our data. And so we take that, and I've got this helper method, clean text, and I say join words equals false, is it's going to return a list, and that list is just going to have the words tokenized from this text up here. So let's very briefly let's have a look at that clean text method. You'll see what it does. The default is to turn it to lowercase. The default is to get rid of stop words. The default is to lemmatize. And so if lowercase, text.lower. Tokens is we're just using the word punct and tokenizing it if the token is alphanumeric. Now for the stop words, we just get rid of the words if they're in the stop words in English. You can modify that if you think some stop words are really important. And then for a lemmatizer, just like what we did above, we're going to lemmatize the words. So instead of having official, officially, offices, and officer, we have like office and official. So now back down here, you can see we're going to run this. And I just want to point out that this right here, because of the clean text, might end up being a bit slow. Again, I think it's going to be about 6 to 8 seconds. And it turns out that was a pretty good guess. Here we have, it's actually just under 8 seconds in total, but it was 6 seconds for the for part of the user, and then 1.7 for the system. That's the calculations, and that's other things that are happening for a total of just under 8. There's a couple ways that we can then do this next step, but I'm using a way called counter right here. So you can see that what we do is counter provides value counts like operation, but not on a series. So if we just have a list and then we run it through counter, then it will return a dictionary where the key is the word and the value is how many times that word was in the set of things that we sent to it. And the reason that we're going to do that is because we don't want a really, really, really huge matrix for our data. It's too slow to compute, and frankly, just too noisy. And so instead, what we're going to do here is I've set a min count of 6. Now, why 6? Why 6 appearances within this? It's a bit arbitrary, but I've looked at the distribution of words, and then you can see kind of the way the count comes down. And by the time we get to 6, we cut off a lot of words. And I think that it's probably going to be really useful for us to do that. But we could be a bit more conservative in this and go higher, so words that only appear 20 or 30 times, or be a bit more generous and look at words that appear even just once. But in that latter case, it will make the data really, really slow. So you'll see what I've done here is we make a series out of the counter, but if you want to avoid counter, here's another way that's pretty much equivalent right here down below. Once I do this, then we can provide some descriptive statistics, and I'll show you how many words are going to be left in our word bank once we've filtered out the early ones. So let's have a look at this. There's in this particular sample, there's almost 13,000 unique words. So that would be a 13,000 by 2,000 matrix, which is a pretty big matrix. But if we want to whittle that down, we can get it down for words that appear at least 6 times down to 3262. Now what I'm going to do is this particular bit of wrangling right here. And what you'll see is that we've created a series where the value of the series is a dictionary in each column. And that dictionary is going to be I in set X for I above min words. So what does that mean? Well, set X is going to be each document. And then I here means for the above min words. So that's, in this case, these 3262 words here, or over 3,000 words. So we're going to have a dictionary with 3,000 entries, and it's going to be the word, and then true or false as to whether that word is in this document. And that's going to be how we get this feature list right here. So once we have that feature list, while I'm here, I'm just doing some value counts on that to see how many are in which kind of question type, and then watch what I do thereafter. Okay, so you'll notice that feature list right here is what we've done is we've zipped up the features and the post type ID. Now, the reason that we want to do that is because if we go back and look here, uh, we have this dictionary for each one of the words. So, this word appeared in this document, this one didn't appear in this document. But then we also want to distinguish which of the two classes this document is. Now, this first one is going to be question. This next one is going to be question. The third one's going to be an answer. So that's what we've done here, is we've zipped up for each document. The first one is going to be that really long list as a dictionary, comma, the second element is going to be whether it's a post type 1 or a post type 2 with question or answer. Turns out we have slightly more comments than we have questions, but those are about the right proportions for for what we would see in this Stack Exchange, which is generally about 1.5, 2 comments for every question. Okay, now we've done what I've suggested down here. We've got our data in the right form. We split it into a training and test set, run the classifier, and let's have a look at the accuracy. But also, down below, let's see, what are the most informative features? So informative features, in this case, are going to mean words that are really likely to be in one class or the other class. So a word that's really likely to be in the questions is going to be an informative feature. A word that's really likely to be in the answers, but not the questions, is also an informative feature. So the accuracy of the classifier here, as we can see, is about 2/3. Let's have a look at the most informative features. So wiki is 8 times more likely to be in the answer than it is in the question, whereas anybody is much more likely to be in the question than it is in the answer. And that kind of makes sense. Does anybody here know anything about this movie? Has anybody else seen this movie? It's very much a very question-oriented word. By contrast, why would wiki be in the answers? Well, because people are using either a specific Wikipedia for that movie or that franchise, or referring to Wikipedia, and they're saying, well, here's a fact about this. If you go to the wiki, you can see something and something. Now, interesting that disease came in here. I'm not really sure what's going on with that, but it seems like it might be a bit of an outlier because of the type of data that we have, or the particular sample that we took. In order to kind of smooth that out, we might do this sort of training a lot of times, splitting between training and test set, and then get some overall parameters for our features, but that's a bit out of scope for here. What I will want to do here, though, is want to show that what happens if we train on the first 1,500, and then we test on the last 500. So we go up to 1,500, and then we test on the last 500. It really didn't change our accuracy score, but notably, now the most interesting features I think are a little more coherent. It seems much less like a fluke, and look at that. Actually, we have this stuff which is like, instead of 8 to 1, now it's 12.5 to 1. And you'll notice that in the comments, words, opinion, and therefore are much more likely to be in the answers, whereas anybody and curious are much more likely to be in the questions. So this won't really reveal a lot about this data set as movies, but that makes sense because movies exist in both the questions and the answers. But the way that people talk about movies is going to be different in the questions and answers, and that's revealed right here. And so we can see here, NLP work can get pretty complex. And much of it is about trying to get a sense of why certain words go together, how many words to train on, and what combination, how certain linguistic features complicate things like negation. And we saw that in the sentiment. This might not be a bad day. And how to label text reliably for abstract concepts, which is a real challenge. You might want to inquire about how to label whether that answer was considered helpful or whether it was considered welcoming. Now, welcoming is more of an abstract concept. We could probably label some words as welcoming, but that would still depend on the context in which we're in, where in some places the same word could be either welcoming or neutral, or maybe not even welcoming at all. So there's lots of work happening in this space in machine learning, where the classifier starts with a pre-trained model, or we train a really big model, and then extended it with users' data. So you could take something like BERT, the BERT model for masking data, and then add new data to it, and that will reweight the model a little bit. So now it won't just classify in a kind of naive sense to your data, but one that really accommodates the various word distributions in your data. Again, out of scope for this chapter, but it would be a really good place to go next if you're interested in machine learning and applications of NLP. But even without using a trained machine learning model, we can still optimize our own classifier by doing things like focusing on relevant differences or using better algorithms, support vector machines or perhaps logistic regression. Even though logistic might seem pretty straightforward, it's just a functional form. Here's all the things that we have as independent variables, and then we try to use that to predict a binary outcome, 0 or 1. It turns out it can be quite nuanced and effective for a lot of tasks. So language is how we communicate with each other. It's how we sort of alter the state of the world around us by sending out information. Now, it's generally encoded as text. I say generally because there are certain specialist forms of encoding which would also account for things like pitch or expressiveness, the way words are breathed or unbreathed, and that's generally the domain of linguistics. But within data science, we do tend to want to zero in or focus in on the text as meaning, at least in the first instance. Now, of course, we can add some of those things back in if we want to, but we generally want to keep it clean for our data to start off with. Now, NLP tends to focus on making sense of text in documents. And so we might think of each document as pre-processed to focus on important features, like we saw in all those cases, whether it's scoring or TF-IDF, we all had to do something with the text first. And then we can score those documents, either by the length of the text, a presence of a word, or using some sort of pre-trained package like a sentiment analyzer, which looks at the words or the combination of them and gives value. We can extract distinctive words, which might help zero in on the most informative words in there, which we could use in other approaches. And finally, we can train a classifier. We can test its accuracy and look for distinctive features between the groups that have been classified, and perhaps use those distinctive features in an inductive way to help us understand the nature of the way those two classes of documents are different. In this case, we would think of or in the example, we think of the fact that the use of the word anybody is much more of a very question-oriented word, whereas a lot of fact-based things like a wiki or a web URL would be in an answer. Of course, classification can be used to predict. Once we have a model, once we have a set of weights, then we can go and predict out of sample, and that's often really useful, and that's why we have some very sophisticated or large pre-trained models, which we then go and use to predict things with them, such as, like I said, with BERT, what would be the most likely word in a sentence if we just mask out one word. The blank was delicious, and in that case, we would predict the word food. And these are viable next steps based on pre-trained models, but like I said, you can get away with a lot of stuff without them. So finally, we have some questions and extensions. So one example might be to download the titles of posts from two subreddits. Now, using PRA or just using JSON, it's pretty easy to get the titles from a subreddit and just have them as their own unique documents. You might want to classify them and report on the accuracy. In that case, you might be interested in not excluding the stop words. There could be some real relevance to whether posts in one subreddit use words like the or of or very or would, and in another they might not use those. But that's up to you to consider. Now, when we do this, imagine trying it out to give yourself a sense of how well this works by doing it first with two subreddits that definitely shouldn't overlap. So we have world news and relationship advice, both subs with over 1 million users on them and tens of thousands of people interacting every day, but on really different topics. So it should be pretty easy to take the most distinctive words and to classify world news and relationship advice. But what if you try that then with two subs like relationship advice and advice? What would be distinctive between the two of those, and how could we estimate that distinction? Would the change in accuracy be really noticeable? Would it be much higher in accuracy? What would the features look like? Now, As alluded to above, try it again, but instead of using all the words, try only the top 500 or so words found using TF-IDF. Now, 500 I just made arbitrarily as a way to express a number, but you might want to do something like report the distribution of the words, and you'll see like a real long tail where all of a sudden it'll flatten out. So these words appear a lot, these words appear generally a fair bit, and then at some point that tail is going to go, and then there's like words that only appear once or twice, and maybe you want to cut off there. Or with the TF-IDF score, the score itself might be some have a really high value, and then the value kind of goes down. And if it goes down sharply, then you might also want to think of a cut point there of some words that are just not very distinctive in the text. Now, we didn't do any unsupervised learning within this, and that's an alternative to, or another variant of machine learning type work, where we might want to classify or cluster the text. A very common version of that is called LDA, or latent Dirichlet allocation, which is a way of classifying documents according to features within the document, so how you would process the words, and then maybe putting them in 5 different categories, and we see which category does this document most likely to fit in. Much like what I discussed earlier in terms of overlapping classifications, LDA actually provides an overlapping classification, but then it cuts that classification off. It's kind of like hierarchical in some way, and then says, well, if we just cut it off here, then we get 5 different groups. And so here's the documents in group 1, and in group 2, and in group 3. But as it happens, that might not be it might not be 5 groups that works really well. It might be 6 groups or 7. And there's ways in which we can try to establish what would be the best number of groups, but I'll leave that to you to explore. That's really it for this section, and I just want to thank you, and you can tune into the next chapter, which is on time series data.